Okay, now we have this question, and first of all, we're relating to, we've got power, which power is the rate of energy. In other words, 1 joule per second, that's in joules, that's in seconds. 1 joule per second is equivalent to what? Is 1 watt, isn't it? 1 watt. Okay, now it says here that first of all I've been given a current and a voltage. Now it says how many coulombs per second are there in this lightning bolt? Well, isn't that also going to give me, can't I say I equals Q on T? So therefore Q is equal to I times T. Now of course T is 1 second. And that's 200 kiloamps. So isn't that going to be 200 by 10 to the 3 times 1? Which is 200,000 coulombs. That's a lot, absolutely. Coulomb seconds. How many coulombs per second are there in this lightning bolt? Well, the thing is though, look over here. We've got...
So does it matter if you scientific notation or just letters?
No, scientific notation. Yep. But remember that this isn't happening, this is per second, but this is happening over what? How many seconds? It's 10 milliseconds. So isn't that going to be 10 to the power of minus 3? Yeah? So in actual fact, your answer is 200 coulombs. Calculate the amount of charge in coulomb contained within this lightning bolt. Let's refer to our formula sheet. How many coulombs for the lightning bolt? How would we work that out? So we have 200 coulombs of charge contained within this lightning bolt. How many joules per coulomb are in the lightning bolt? Let's think about it though. Think about joules per coulomb. Isn't there another joules per coulomb? Doesn't that relate to something? Voltage maybe?
Yeah.
What's the voltage? 1.2 megavolts. So, we've got energy, or work, we've got VIT is equal to what did we know from the textbook? There's an energy one, which was what? Wasn't there a one relating Q, E and V? What did we have? Did we have that? So voltage is equal to that. Energy, Q, yep. So V equals E on Q. And the energy how many joules per coulomb? Wouldn't that just be the voltage? Yeah. So the voltage is 1.2 megavolts. So that is 1.2 by 10 to the 6 joules per coulomb. Now it says calculate the total number of joules carried by this lightning bolt. Well, we can say that's E is equal to V times Q. Which is 1.2 by 10 to the 6. But a coulomb of charge is what? Isn't that... Is that Q, is that the coulombs, or is that the charge of one electron? We're not looking at electrons, are we? So Q is 200 times 200. So that is 200 times that is 240 by 10 to the 6 joules. And of course the power in kilowatts. Well, power equals VI, which we have a current of, what, 200 kiloamps times a voltage of 1.2 megajoules. Now what's that? That's going to be 240 by 10 to the 9 watts, which is what? How many in kilowatts? What would that be? Wouldn't I have to divide through by 1,000? So that would be the same as dividing through by 10 to the 3 kilowatts. So I've got 240 by 10 to the 6 kilowatts. In particular though, now it says here define current and voltage. Well, what is current? First of all, let's have a look at it. I equals Q on T, that will tell you a lot. It's the... So we can say that it's the charge that passes through per second. So in other words, 1 amp is 1 coulomb of charge per second, isn't it? And voltage, I'll get you guys to do that. This is what I really wanted to look at though. We've got two different circuits. Each of these globes has a resistance of 4 ohms. So first of all, if I wanted to find, we want to find the total resistance of this circuit here. And to find the total resistance of that circuit, that is of course in parallel. So if we refer back to, and it's on your formula sheet, you will see this. And adding resistors in parallel, first of all, the total resistance of those resistors in parallel are always going to be less than the smallest resistor. So if I had 3 4 ohm resistors, then it's definitely going to be smaller than 4 ohms. Let's have a look exactly what it is. So over here, I've got a 4 ohm resistor, a 4 ohm globe with a resistance. So in order to find out what the current is through that circuit, we need to work out what the total resistance is. So first of all, we've got, using from our formula sheet, 1 over the total resistance is equal to 1 over 4 ohms plus 1 over 4 ohms plus 1 over 4 ohms. Now, that's 3 over 4, isn't it? But that's not my answer. That's 1 over r to the t. So what you can do to the power of -1, if it's a fraction, we can just flip those around. Or we can do that to the power of -1. So the total resistance is 4 over 3 ohms. What about this though? What's the total resistance in parallel in series? we just add them. Okay, so the total resistance of circuit B is 12 ohms. Which of the circuits shows the lights in the series arrangement? Obviously that is B. Determine the potential difference across each light globe in circuit A. Now, it's important to note that over here, if I've got 12 volts and I've got 3 things, what would a voltmeter read here? What would a voltmeter read here? No. 4 volts. Okay, the energy would be evenly dissipated throughout those, so each of those would say 4 volts. So in other words, in a series circuit, the voltage divides, doesn't it? Okay, with voltage splits up. Now, one thing I will say though is that over here in circuit A, and this is why we tend to do a lot of things in parallel, is because each of those globes would be accessing 12 volts. But what would happen is that over here, think about it as water flowing, some of the current is going to go through there. A third of the current, because in this case, because of that, they all have the same resistance. Some is going to go through there and some is going to go through there. What will happen in a series circuit? The current, each one of those the current will pass through each of those. So determine the potential difference across the light globe in circuit A. Well, in order to do that though, let's find out. We know that the total... First of all, we can say that V equals I times R. But we don't know what the current is yet, so let's find out what the current is. The total current is equal to V on R, which is equal to 12 on, well, in this case, the total resistance of that circuit is 4 on 3. If you like, I can do that. 4 divided by 3. How could I change that sign? Now, of course, you can do it in your calculator. Change that to a times. What do? Flip that around. 12 times 3 is 36. 36 divided by 4 is 9. So, we have 9 amps going through. Now, what's going to happen? I've got 9 amps. If I put an ammeter here, that's going to read 9 amps, isn't it? But where's the current going to go? Is it all? We're obviously, given it's got the same, we're going to have what? 3 amps going through here, 3 amps going through here, and 3 amps going through here. Now I can use Ohm's law, because the voltage across each of these resistors is the current across that resistor times the resistance. And the current across each of those resistors is 3 amps. So it's 3 times, and that resistance is 4 ohms, which is equal to 12, isn't it? Okay? So each of those are going to receive 12 volts. Determine the potential difference across the light globe in circuit B, however. Well, let's do it. What is it? Over here, I want to find the potential difference across here. So, is the current for this circuit going to be the same for this circuit? No, it's not, so we have to do it again. We can say that the current is V divided by R, which is 12 divided by 4 plus 4 plus 4 is 12. The current there is only going to be 1 amp. Now, that means that each of these globes also receive 1 amp. Which means that when I'm trying to work out the potential difference across each of these globes, since they all have the same resistance, which is 1 times the resistance, which is 4, which is 4 volts. So if I've got 3 equal resistances and 12 volts, then each of those are going to read 4 volts there, 4 volts there, when connected in parallel, like so. So what do you notice? Over in circuit A, parallel circuit, the voltage is the same across each of them. The current is split, And it's the most important thing for you guys to understand, and particularly for your test. For circuit B, the current is the same through each of them. However, the voltage is split across each of the components. Calculate the current through one of the light globes in A. Well, we've worked that out, haven't we? 3 amps. A lot of the time you can answer subsequent questions because you needed to work it out anyway. Calculate the current through one of them in globe B. Well, we worked that out to be 1 amp, didn't we? Calculate the amount of energy lost by an electron as it passes through a single globe in circuit B. We could do that. A single globe in... Now, we've got to obviously relate this to how many electrons. What was the formula we had? Didn't we say that the number of electrons times the charge of one electron is equal to what? What was that equal to? What was that equal to? Has that been given to you? Not sure. So that seems to be missing. What will that give you though? Number of electrons times the charge of an electron. Isn't that the charge in coulombs? Amount of energy lost. So we should get that, which is what? That's 6.4 by 10 to the power of negative 19 joules per electron. And if I multiplied that by the number of electrons, we could revert and get back to there. Calculate the power dissipated by a single globe in circuit B. Well, I could use P equals VI. And we know that the voltage is across each of those globes is not 12 volts because it's in series, it's 4 volts, and the current was 1 amp across each of those. So therefore the power across each of those globes was 4 watts. Now which one would be brighter though? Which one would be brighter, the series circuit or the parallel circuit? Well, the series circuit, we're going to have 4 watts across each of those. Yeah? Let's compare that to over here. What have I got? I've got 3 amps going through each. 3 amps, and I've got a voltage supply of 12. So I'm going to get, if I measured the voltage across there, that's going to be 12 volts. But it's also going to, if I was to read the current through there with an ammeter, that's going to be, didn't we work out to be 3 amps? So therefore, the power across a globe here is equal to 12 volts times 3, which is 36 watts. So which one's going to be brighter? Isn't this one going to be brighter? Yeah, more power crossing. So globe, so circuit A since the power across each globe is 36 watts, this compares to, didn't we have 4 watts for each? This compares to 4 watts for circuit B. All right, we'll carry on. I know that we're going to do more of this, okay? We'll go through and we'll do more of this next time. What type of device is this? Ohmic or non-ohmic? It's a non-ohmic. And it's a non-ohmic. Why? Because the IV relationship is non-linear. That would be enough. We'll skip that question. Let's have a look at this one. Now, I'd like you guys to have a go at this. And this time, remember that we're using the formula. 1 over RT, the total resistance, equals 1 on R1 plus 1 on R2 plus 1 on R3 and so on. We obviously stop there. Have a go at this, please, to work out what the total resistance is. Another way of doing that is, in your calculators, we can do that to the power of -1. To the power of -1. So have a go. Now, first of all, we've got 3 resistors in parallel. Can you tell me what value it's going to be smaller than? It's going to be, the total resistance of this is going to be smaller than the smallest resistor. So it's going to be smaller than 25 ohms. So if you get something greater than that, then clearly you have made a mistake. So how I do it is I do this. I don't necessarily use their rule. I say that (1 over 50) plus 1 over 150 plus 1 over 25 to the power of -1. If I was to do that straight in a calculator or a CAS. I'm not sure if you're, depending on the scientific calculator, you should be able to do that, okay. No, scientific. You can't use a CAS calculator in your Year 12 physics exam, so get used to using your scientifics. If I was to do it by hand, though, common multiple of those is 150, which means if I wanted to get that 150, I'd have to multiply 50 by 3. So I could do it by hand, if you like. And I've got to multiply that by 6 to get 150. To the power of -1. 6 plus 3 plus 1 is 10. And if I was to do it to the power of -1, that's going to be 150 over 10. Which is equal to, you should have got 15 ohms. So those 3 resistors in parallel have a total resistance of 15 ohms. Now, Once you've found that, how do we work out what the current is? Well, for starters, we've got to work out what the total current is. And the total current is V divided by R. The voltage across it is 4.5 volts. And we know that the total resistance of those is 15 ohms. So I should get a current. We don't really... Now, this is probably going to help us for later on anyway. But what can you tell me? Do we really need to find the total current? What can you tell me about the voltage across each of these resistors? It's what? What's the voltage across each of these resistors, Matt? Well, what's the voltage of the supply? 4.5. So what's going to happen? Are each of them going to receive 4.5 volts? That's current. So some of the current's going to go through here. Some of the current's going to go through here. Where's most of the current going to go through? Which resistor? Isn't current generally more current going to go through the path of least resistance? Yes? Okay, let's try and do this without calculating. Let's just, because we know that current is equal to V divided by R. Smaller value of R means more current. Now, if I was to split this up, we can say that this here, there's going to be 6 times the current going through R3 as there is R2. And there's going to be twice the current going through R3 compared to R1. First of all, if we find what the current is, we know what the total resistance is, but at the same time, we can use V equals I times R. Now, the voltage across each of those resistors is 4.5 volts. The resistance at R2, so in other words, we can say that the resistance at R2, or we can say that the current in R2 is equal to the voltage across 2, which we know is the same, across R2. That's going to be 4.5 volts over 150. If I was to do that, I'll work that out. Yeah, we'll do that. 4.5 divided by 150 is 0.03 amps. 0.03 amps. What about if I wanted that in milliamps? Well, I guess we don't because that's okay, like so. Now, if 0.03 amps goes through, let's think about it. If 0.03 amps is going through here, didn't we say that R3 would get 6 times the amount? Well, let's work that out. Let's confirm that. Let's work out the voltage or the current across 3. Well, that's the voltage across 3, like so, which is 4.5 divided by 25. And if I do that in my calculator, .18. So we can see here that 0.18 or 6 times 0.18 amps is going through there. So what's this missing part? What's this part here then? Isn't that going to be 0.09 amps? I think it might be.